Hey, what's good, y'all? Link here. And let's go for another daily legal question. Question 2040. Kth smallest product of two sorted arrays. Hard one with 48% acceptance rate. So let's care about this one. Let's see how this one goes. Uh, doo -doo -doo. Grab the code. We're gonna have two lists of numbers and digit k. The kth. Okay, let's see. Given two sorted zero index integer array, number one and two, as well as an integer k, return the kth one based smallest product of nums index I times num2 index j, where I is between OK, j is between OK. Return the kth smallest product. Smallest product. OK is equal to 2, so uh, what's answer here? 2 times 4, 5 times 3. Okay. Okay. So let me take it. Oops. Let me take a screenshot of this whole thing. Uh, the two smallest products are actually. Oh wait, what? 2 times 3. Oh, we can have the same number multiple. Oh, 2 times 3, 2 times 4. Oh wait. So this case will be shouldn't be -4 times the whole thing, and then 2 times the whole thing, and then we start with 0 times the whole thing, and then 3. Since they are sorted, if we want k, we want to. Okay, so since we can reuse the element, I would say that the smallest product will be just the first element times everything, and that will give us 2. So I think we can divide k by nums, the length of nums2. In this case, will be 6 divided by 2. And then we also need to take the remainder of that too. So 6 divided by 2, that is equal to 3. So you're going to use three numbers, 0, 1, 2. Yep. And then times the remainder, which is 0. 0 times 2, right? No, it's 0. The remainder plus 1. Wait. 1, 2, 3, 4. Oh no. Yeah, it's the opposite. Yeah. It's the length minus the remainder because we go in the opposite. Okay, yeah. That work? Makes it easier because it's sorted, right? So thinking about just oops. Um it's gonna be kind of like an offset, I think. You're gonna you divide the k by this, and then you have also the remainder of this division, and then you're gonna do nums1 and index 1 the division, which in this case is 3 minus 1, so 0, 1, 2, times nums index I and the nums index length minus remainder, right? Is that it? I'm scared because it seems too easy to be true, honestly. Okay, let's see. Um, let's see. Num1. Let's see. So offset. 1 is equal to k divided by um let me do, and 1 is equal to like num1, num2 is equal to like num2. So k divided by num1, that's the offset. And we also want the offset remainder. Let me do this, is equal to k mod 1. Yep. And then we're gonna return wait, we want divided by 2 actually, right? Oops, 2. And then also put 0 here. I don't think we need any 1 in this case. Okay, so we're gonna do return nums1 index offset 1 minus 1 times nums2 index length of nums2, which is equal to n2, uh minus offset r minus 1, right? Because in this case we have we have the remainder is 0, so the size is 2. So 2 minus 0 is equal to 2, but we actually want 1. Yep. I don't think that's all. I'm probably misunderstanding the question if this is the solution. Oops, if I get something wrong here. Yeah, missed something. Let's see. I mean, at least those worked. Okay, so for the third one, oh my gosh. Oh no. We have negative numbers. Oh my God. Hey, now that we have negative number, now okay, now that's hard. I forgot about that. Because the oh my gosh, dude, the problem here is that how do we oh my gosh, because we can have the negative times a positive, which is I think always what we want. When we get a negative, we always want to get oh when we get a negative, we want to get the positive. 0, 1, 2, 3, 4. And then when we get a negative, we get a second positive. But now we don't want this. We want because now we reached wait, negative times this, negative times this. Now we're doing 2 times -3. Oh, okay. Now this is hard. Yeah. Like, that's why the question is hard. Okay. Uh, hmm. Now I see why the question is hard. I grab this example right here. Oh my God, I have like a highlight. All right. Okay. Now this is hard. I think what we want to do here, mm, I'm thinking if I can separate those and then Then we're gonna multiply the negative with the positive, and then the negative with the positive. But let's say we only have positive and negative integers. That won't work. Like in this case, it will be this times nothing, this times nothing, right? Think if I can use some sort of like try to approach this problem. Maybe put like in a mean heap or max heap. And then but that's the thing, because maybe we don't want to multiply the most negative with the most positive. I mean, we do want that, but we will reach a point where, for example, in this case, let me create this thing. Okay, so, oops, oh my God, dude. Okay, there you go. Like in this case, we go negative 2 times 5, negative 2 times 4, but we don't want to do negative times negative 2 times 2 because that's negative 4, and then we do have a smallest number in this case. Wait, smallest product. Why it's not? What about negative 3? Oh, that's positive, my bad. Okay. And then we have 2 times. Oof. We could have, okay, so negative 10, okay, negative 8, okay, this is negative 4. But we have a negative 6, which is negative 2. Wait, it's 2 times negative 3. Yeah, that's the thing. So now how are we going to do this? Hmm. The smallest product. Okay, how do I know that I want to switch? Hmm. Oh my gosh, at this point, I have no idea how to approach this problem. Like, no, zero, zero, absolutely zero. Like every single thing I try to think about doesn't work. Thinking about putting like a try, like a mean heap doesn't or maybe like separate mean heap and max heap, that doesn't work because like in this case, we were at 2, negative 2, and then out of nowhere we just had to jump into 2 so we can get a negative 3. Or maybe we can, since it's already sorted, we don't need to try. We can use a stack, right? Yeah, I think we can use a stack. Um, or maybe we can use a stack. Putting like the opposite, we pop left, negative 2, and then we pop right, and then when we want, so at some point we want to switch to negative 3, that's the problem. And then we can't pop because, oh my gosh, because we're at some point we still want to use the 5 on the right side, for example, to multiply maybe with 0, right? Yeah, so we don't want to use tag because that's gonna pop elements before all of the other elements use it. So I'm not gonna use a stack. Think about a two pointer, but two pointer may not work. Okay. Okay, so two pointers work. Mm. Oh. Maybe let me try the first example right here. Maybe the first example might help that. Because the first example is pretty straightforward, right? You grab the minimum one multiplied by three, minimum one multiplied by four. The problem is the moment we get negative numbers, which is in this case it's the first. But even in this case, like it's gonna be always the same thing. Yeah, yeah. This is the problem that we have. Yeah, this is the problem. Uh, yeah, I have no idea. Huh. Um, okay, so we decided to multiply mm, -2, 5, -2 with 4, and then -2 with 2. That's giving that gives 4. But we actually don't want that. We want to do 2 and multiply with -3. How can we make this switch? How can we make this decision to move from -2 to 2 and move from 2 to -3? Oh, oh my gosh. Well, I have no idea how, like, I don't have any solution to this one. I mean, besides brute forcing the whole thing, picking out the products and then sorting them and then returning the element index k minus one. But other than that, hmm, I'm totally stuck in this one. Like, totally. Um, that way, is that a way we can save the smallest number, the largest number, the smallest number, the largest number, and then uh the smallest number on the left multiplied by the largest number on the right, and then we keep doing. And then we have also the smallest number on top is this, and then 4. But when we get to 2, 2, 2 times -3 is actually smaller. Then we switch to 2 times -3, 2 times -2. Oops, 2 times -1, but that's -2. And then we now have -4, so we do -4. -2 times -1, that is positive, but we have -2. So this goes right here. And then we have -1 times -2, which is 2, and then we have 2, 2, that's 4. Ooh, okay. Maybe that might work. And then in this case, who is the smallest? Oh, I think I crossed, but yeah. Maybe that works. We have left one, right one, right one, right left two, right two. We always would compare those two multiplications, and then we move the pointers inwards. Now, what's the problem in this case? We might not be able to get out the k element. What is k? K is probably like super. Yeah, it can be the whole thing. Okay. Yes. Okay. Okay. Yes, the constraints are pretty big. Okay, so I think let's see. So we have. Let's do left. This is the greatest one. We multiply with this, and then we have the red, which is this multiplied by this. So let's see. -2 times -5. That's good. So we boom. Ne -2 times 4, that's good. So boom. Now this is better. So boom. Which one's better now? -4 or -2? -4. So we go boom. Which one's better now? -2 or -2? -2. So we do boom. And then which one's now? That is gonna be this one. So boom. And then which one's better now? This one. So boom. Now this is gonna be out of bounds. Once this one gets out of bounds, we're gonna move to this and reset to 5. Oh, but that is not good. Oh my gosh, that's wait, okay. I was close, but I think let's see. Oh, maybe wait a second. Let's start at the beginning. So let's do this for reference. The red moved right, and then the white moved left. Okay, just for reference. Uh, okay, so this is better, boom, this is better, boom, this is better. Hmm, we have to manipulate those two pointers accordingly. Okay, okay, so now, okay, this was better. Now this is better, right? Do I want to move this here already? Boom. Which one's better? -2 or -2? Doesn't matter. So let's do this. Boom. Actually, yeah, in this case, I don't think it matter. If it's equal, I don't think we have to move this. Now, which one is better? It's the white one. So, oops. Boom. Boom. And then which one now is better? Oh, right. If the red is better, the white is better. Boom, goes to here. And then which one's better now? -1 to -1. That's 1, 1 to 2. Okay, this is better. So the left goes here, goes here. This is right. I don't think this is right. Okay, so let's see. It's here. Oops. So the elements are sorted, right? Well, I think we can do this, but once we reach a 2, what does that mean? That means that the the smallest number, the largest number in 1 multiplied by the smallest number in 2 gave us a better answer. Okay, so at some point we need to reach a zero, right? Yes. So let's see. So think maybe we don't use this. Maybe let's use arrows. I think it's better. So the white right here, the white is right here. Oh my gosh, those are horrible arrows. White is right here. White is right here, and then we have a red, which is right here, and then red is right here. Yep. And then we can increase those. Oops. Is there a way to increase this? I don't think. Okay, this is fine. Okay, so maybe let me go the red the opposite way. Then we can do this, and then same here. Then we can do this. Okay, so we don't have to overlap those. Okay, so we multiply by this. This is better. Boom. This is better. Boom. Now this is better. So boom, right? Now which one's better? -2 is better. Yeah, so oops. -2 is better. So boom. Which one now is better? Wait, no. My bad, my bad. Which one's wait, let me oh my God, this is confusing to walk through. Okay. Uh which one's better? -10, so we're gonna do negative oops, let me go a different color right here. -10, oops, -10. Boom. Now we have -8. Let's do -6 already because this is the answer, right? So -2, -8, and then now it's going to be -6. So this one goes right here. Uh, now which one's the answer? Now the answer is -4 compared to -2, which it will be -4. -4 wins. Boom goes right here, and now we have -4 right here. And then who wins now? -2 times negative. This is 2 time compared to -2. So this one wins again. So boom goes right here. And then -2 goes right here. And then who wins now? Now now it has to be 0, right? Now it has to be 0. So that was not right. Hmm. And -4. Maybe let's see. Hmm. Okay. Wins, wins. But we have to keep 2 right here. This goes, this goes here. Do I want to move here? I don't, because I still want to do -2 times 2 at some point. Wait, why did I move? Okay, so at this point, -6 wins, okay? Yeah, but I still want to do -2 times 2. Um, oh wait, no. Now there's -4, right? And then the bone goes here. Now it's -1 times -2. Goes right here. We go -2. And then this is -1. Da, 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 da. We actually want to move this to here now, right? Hmm. How, like in this case, we got to pause. Okay, so this is not gonna work. Yeah. Okay, this is not going to work. What you call? Okay, there you go. Oh, mm, now I'm thinking about this. Maybe we can use some like we grab all the negative numbers, we grab all the positive numbers, grab the positive number, grab the negative numbers, multiply those. Um, uh, yeah, I don't know. I was thinking about sorting them, but that's gonna be super inefficient. So yeah, this one I have zero idea how to approach. So I'm gonna look at least at some hints and see where it can go from there. I wonder what people think about this one. We split this problem into four cases depending on the sign of that's what I was thinking. Binary search. Oh, I thought about binary search before, but I wasn't able to find a way of using it. Okay, so how can we use binary search in here? How can I use binary search here? So we divide into positive, 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 negative, right? Oh, positive, 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 negative, negative, positive. Oh, yeah, and then negative, negative. Um, how can we use? Okay, so positive, positive, and negative, negative, they're gonna give the same answer. Yeah. So, so if we get, oh my gosh, I opened it Python for no reason. So if we grab negative with a negative and then positive with a positive, we gonna compare the same way. Yes. Okay. How can we use binary search here? Maybe I, hmm, negative with negative, positive with not positive. But we actually want to do first. Uh, I actually want to do negative, positive, negative, positive first, and then let's see. In this case, we're gonna have this and this. So it's gonna be, oof, it's gonna be -4, -8, -10, and then oh, this is why is it two? Okay, so it's gonna be. Let me actually write this down. The okay. In this case, we're gonna have -4, -8, and -10. And then on the other side, you're gonna have, oh, it's positive. Yeah, yeah, yeah. Yeah, the zero case, I mean, it's gonna be, yeah, we're gonna have like 0 times all the 1, 2, 3, 4, 5. Here we can, don't count 0 in this case. Okay, and then we're gonna have 0, 0, 0, 0, 0, right? 1, 2, 3, 4, 5, and then we're gonna start doing the other way. So, -3, -1, -6, -2. Yeah. And then once we're done with this, then we're gonna start doing negative, negative, positive, positive. So are those the cases? So negative, we always want to do negative positive and then positive negative first. And then we have positive positive and then negative negative, right? Do we need to care about the zero case or oh I don't think we do we don't need, oh yeah, yeah we can just add as a positive that's okay yeah. So we don't actually worry about this. It's gonna be like here, right? Yep. So now that we have this, no, I actually didn't do the whole thing, but this shouldn't even be here. Okay, there you go. So these are those two. So this is this and this. Now we need a positive, positive, negative, negative. So how can we use binary search here? Oh man. Okay, so how can we use binary search? Because like I mean in this case, since everything's ordered, we can actually let's see. I mean, in the worst case, we will still have to let's see. Use binary search, dude. Oh my gosh. Okay. Uh, I mean, in this case, in the worst case here, we can stop early when we get to k elements because we are building them in a ascending order. But the problem here is that in the worst case, we will still have to go through every single product in the arrays, and that will be in squared, which is not good, right? So that's I think where binary search comes into play, but I don't see how I would use binary search in this case. I could use here, but why would I use here? I don't think it is an option to use binary search. Uh, yeah, the only way I can see binary search being a fit is right here in this case. Or maybe another thing is like if the length, we do length maybe? Because like, okay, so if the length of this, and we start in the middle, if the length of this, it's, because we can do what we can do here. Oh, but the problem here is that we have to separate those two, and we know that these are greater than this, but we don't know if those will be in order, right? So we need to check where we're gonna get number from. Um, okay. So maybe we can do maybe that's the binary search part. We don't need to calculate the whole thing. We just need to grab one of those problems, right? So we go here. Is this greater or smaller than k, the length of this? If it's smaller, then we go to here and then we update k with the size of this. Now this is good. If the size now of this is good, Then we need to find exactly here, and what will be, it's, oh no, wait. That's a problem because we don't know if we have those in order. We can have some element in here that's smaller than here. That's why. Uh, hmm, that's because we have to use. Oh wait, I think we can take this as a whole thing and this in the whole thing, and then we check whether the answer is in here or in here, and then in in one of them we can just do a point approach, boom boom, and then check which one's greater. We'll add to the answer until we reach K. I mean, we have to compare the numbers to make sure. Yeah, we have to. This might work. Let me try to code this thing. I'm 42 minutes thinking about this. So first of all, we need to separate the positive and negative numbers from both arrays. So pos one is equal to this. We have 2, 3, 4. Pos two, uh, yeah, pos one, pos two, negative one, neg one, and then neg two for, oops, for number in num1, if number is greater or equal to 0, pause one dot append number, else pause two dot append number, and then we do the same thing for two, oops, num1, pause one, and then this is neg one actually. And then for num2, pause two dot append, and then neg two. Yep. Pause two dot append n. Okay. Pause two and the negative thing. Now we need to check what sub subproblem group is our answer, right? Is it here or is it in here? Um, so if length of, let's see, in this case, this and this. Okay, so negative and positive, positive, plus. Okay, so let's say we have two numbers here, two here, two here, two here. We have two, this is four numbers, this is four numbers. Yeah, we can use, I think, K is exactly K. So if length of pos one uh, times length of pos two plus length of, wait, oops, doing pos negative first, times length of neg two plus length of pos of neg one times length of pos two. If that's smaller or equal to K, that means in this first group, else in the spec group, right? I can do this, okay. Okay, so length pos one plus times length negative two, so positive, positive, negative, negative, positive. Okay, so that means that it's in the, otherwise gonna be either positive, positive, negative, negative, right? So if it's in here, Uh, actually, we can do like a. Can we do like a helper function? Def find a, which is equal to re1, re2, and then I'll implement that later. And then if it's the first one, then we can just do hmm. Now the problem here is that if these are 2 pointers, we actually have to do 4 pointers. Okay, so we need re1, pause, pause, r, pause 1, r, neg2, r, pause 2. Oops, actually, I'm like, it's going to be, we're going to multiply re1 with r1. So r1 is looking to re0, re1, re2, re3. Yeah. And in this case, we're going to do return, find k. We're going to multiply pos 1 with neg2, and then neg1 with pos 2. And then k is equal to the scale normal. And then this returns an integer. Else, return find k, going to be pos 1, pos 2, neg1, neg2. And then I mean, I should put this in a whole different thing, but it's gonna be k minus this whole thing. Yeah. Oops, did I? Okay. Okay. And then here we're gonna do res is equal to this, while length of res is less not equal to k. Um, we need the pointer, right? So left 0, left 1. We want to multiply. So this one's negative, positive, negative, positive, negative, positive, positive, negative. So we're gonna have a pointer one here. I mean, it's the number, it's what we want to multiply, right? So I always want to multiply. Okay, so um, always multi 0 with 1, 0 with 3. Yep, doesn't matter. Okay, yep. So left 1, 2. Mm. Yeah, sorry. I can do I actually, right? I0, I1, I2, I3. 3. And then you go to, oh, you're going to 0, right? 0, 0, 0, 0, 0. And then y res equal to this. Let's see. We want to multiply this with this, with this with this with this, and then okay, so we're gonna okay, so it's gonna be -2 times -2. And then that moves a little bit. Once we reached -2 at the end, okay, so and then, okay, so let's do this. If I1 is greater mm, and I0 is smaller than length of R0 and I2 less than length R2. Okay, so the two arrays that we started multiplying. Okay. Yeah, they're sorted, right? Okay, yeah, they're sorted. Okay. Now, if if I1 is greater than greater than length of R1, then I1 is equal to 0, I0 equals 1, and then the same thing with the other ones. So if I3 is greater than length of R3, then I3 is equal to 0, and then I2 equals 1. And right here, we choose the return rest of -1. Okay, so while length of k of the response not equal to k, and I0 is less than length of A0, and I2, if I1 is greater than length, greater or equal to length, uh, or equal to the length of A1, that means we reset that, increment I0 by 1. If I3 is greater or equal to the length of I3, we reset that, and then I2, we multiply by 3, we increase by 1. Okay, now as we compare, prod those product 0, 1, it's equal to array 0 index 0 times array 1 index dot 0 index I0 index I1, and then prod to oops 3 is equal to array 2 to 2 3 3, and then if prod 1 is smaller than prod 2 3, then res dot append prod 1 I1 is equals 1, else we're gonna do the opposite, so do 3, and then 3 plus 1, yep. Yep. Okay, so we get the product, check which one's smaller, and then we have to increment after that. Yeah, we should be fine. Let's see how this one goes. Zero confidence on this one. Okay, list our range. Oh, we can. Oh, in this case, yeah. But we k is equal to 2, right? So that should go where? Here. Oh, okay. Now we have to do one thing. Hmm. Because we can have. Oh my God, we can have multiple cases right here as well, right? Like, Wait, but length? Okay, so this one, pause, neg. What are the cases? My God, we have a lot of check here. Let's do infinity. What if we have +1, +2, and -1? That's it. Well, that's fine. Yeah, we can do. Yeah, we can do. If uh, if R0 and R1, then this, else uh, if R0 1 is equal to array 0, xi 0, else dot 1 is equal to array 0, array 1, and 1, right? Yep, 0, else 1. And then we do the pretty much the same thing for here. So if R2 and R3 and this, oops, else if R2 and prod2 is equal to going to be this, else prod is going to be 3, 3, right? Might get an infinite loop right here, but we'll see. Okay. Okay. Let me see what I'm multiplying here. R0, R1, R2, R3. Let's see. Yeah. R1, R2, R3, 0, 1, 2, 3. 0, A, 2, 0, 1, 2, 3. So 3 is going to be this. If array 3, blah, blah, blah. If prod 1 is less than prod dot, rest dot append prod 0, 1, else blah, blah, blah. I don't have anything. Oh, wait. Do we even get to this loop right here? Okay. Because those are, we don't even get to this point right here. Oops. Let me, oh, maybe this is an OR, right? Yeah, I think that was an OR. List ranges. I don't think this is the right way of doing it, honestly. Wait, but yeah, R0 should be this. So prob one, array 0, index I 0. Mm. Um, oh, that's why. But can we take, maybe, maybe. Still out of range. Because I don't have, yeah, I'm not, uh, yeah, I'm gonna look at solution because I don't even think this is the right way of doing it. What's the acceptance rate of this one? Acceptance rate is 48. Jesus Christ. Okay. When a question's hard like this, I doubt there's gonna be any useful comments in the discussion. Let's see. That's the binary search part. And then numbers one is equal to this, numbers two is equal to, okay, so generate our product. Our product is this. Binary search setup. Maximum possible product. Wait, so you do generate all the products? The problem requires find the case product formed by multiplying every element on the one with every element on them two. See the zone number is going to be in times n. A brute for approach computer would take time, which is a but instead we use binary search in the answer space combined with nested binary search to count how many products are less than or equal a given value. This reduces the time complexity to where max price the range, blah, 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 blah. Okay, so initialize left, use okay, okay, covering all the possible products. Well, left, less, right, compute mid, okay, count is equal to count less or equal to number one mid. If count is less than k, the k amount present is larger than the mid, then set less equal to else the count products less than or equal to okay, count less or equal. For each number one in each number one in number one. Case one number one is equal to 0 if target all numbers 2 may contribute, so count plus case 2 number one is greater than 0, binary search to find larger than 2 or less than equal to target. This counts blah, 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 blah. Case 3 blah 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 blah. Number one is less than 0, then binary search to find the smallest number 2 j where and the product is less than equal to target. Let's see. This okay, so these two parts I didn't understand at all. Let's see. So binary search to find the okay, so I see number one for each number one nums one. If number one is equal to 0, we have a target. What is the target? Nums one, nums two, and have the oh, the target is the mid. Okay, is the target the mid? I think so. Let me see if the target is actually the mid. Okay, is the mid? Okay, yeah. Okay. Okay. Binary search to find the largest nums2 index j, where num1 times nums2 index j is less than target, or equal to target. Binary search to find the largest. Num1, if num1, okay, case 1, num1 is equal to 0. If the target is greater than or equal to 0, then all num2 elements contribute to the count. Okay, count. Okay. If num1 is greater than 0, then binary search to find the largest and num2 card element, where the num1 times that element is less than or equal to target. This count is low. The count is low. Number of elements less than target. Okay, let me go through step by step here. The second smallest product is 8. Actually, I want to look at the code. This is not really clear to me. Well, let's see. Okay, so first of all, left, right, while left, left, and right means going to do. Okay, so these are the actually. Okay, so the mid is the current candidate to be the answer. Okay. Um. Oh my, why am I using? Yeah, okay. So count parse. Da, da, da. Wait, this is the okay. While I okay. Wait, high is equal to greater than low. Okay, okay, that's fine. Now this is what getting me. Count pairs. Okay. For each number in nums1, if the number is greater than 0, then do we want to, what is bisect the bisect right? I have no idea what that is. What's Python bisect? Left A, X, low, high. Lesson module in Python provide a function for inserting elements into a sorted list while maintaining the sorted order. Okay, it achieves this efficiently by using binary search algorithm to find the correct insertion point. Okay, this function returns an insertion point for X in A to maintain sorted order. If X already exists in A, the return insertion point will be the da da da. So what is low and high in this case? What's the low and high in this case? Oh, there you go. Um, this is a range, right? Probably. Yeah, yeah, that makes sense. Okay. Bisect the bisect right X. We're gonna insert nums two. I would just sort those if they are already sorted. But okay. Bisect or bisect right? Oh, bisect right. It's not bisect right. Oops. Oh my god, I can type. Okay. Go to bisect left, but return insertion point, which comes up to the right of any existing entry of X in the array. But what is that the like what is the insertion point? Okay, by default, the term list is used. If there is ever an edge, the insertion point will be before the return value is suitable for use as a first parameter. Let's insert assuming. Oh, it's the indexed index that this element will be inserted. Okay, so now why did you divide x? Okay, we have a column right here. So a times b less than or equal to x, which is greater or equal to b. What the hell? Okay, why are you dividing x by 8? So x is the number that we are trying to find, and a is the current number that we have in nums1. Oh, so you're trying to find a nums2, but why are you using bisect? I mean, you have a target x, right? And then for each number num1, you want to divide by a, so you can find the matching product on nums2, right? That's why I divide. But then like, oh wait, you want to find the point of the array where that element might be, and then you grab every single element before that, the length of that, and add to the count. I don't know why would you do this though. So this is a really hard question. Oh my gosh. Like the solution is not that big, but this is really hard to come with. Uh, that's why I use bisect left. Okay, and then you do this. Okay, that's why you want the largest number in this case, and then the other one you want the smallest one. Okay, possible, right? Yeah. Hmm. This is even harder. Target is equal to x. And there's no way. Like I have no idea what's going on here. Like countless. I mean, targets is this. If x mod a is not equal to 0, careful with that. Okay, seal. Okay, seal is fine. And count plus bisect the bisect left. But we wanna insert that target number into. We're gonna find that number in nums2. We wanna find that number in nums2. Okay, so one thing that I saw here is if for each number 1, if target is greater or equal to 0, all numbers contribute. Okay, if number is greater than 0, then binary search to find the largest number. Yep, and num2 where the product is less than or equal to the target. Okay, that's why you use the bisect. You find the target and then you do the bisect. This is the first time I'm actually using bisect in a LeetCode question. That's why I'm getting a little confused about it. Okay. Okay. Bisect numbers, and then we find this is the target, and then if it is less than zero, we did why this part we did the module. So x mod not equal to zero. Um, I wonder why we had to use in here. Is it because we're not using it here? And we have to. Oh my god, this mod is not equal to zero. And okay, then we're taking the ceiling. Okay, I don't know why we didn't take the ceiling in the previous one, but okay. So count plus equals. Okay, so we need to bisect to the left of that one, and then hmm, if the count pair is less than k, what does that mean? Oh, is it the number of products? Oh, wait. Let me read this one again. The largest number num and x1 is less than equal to target. The largest num. So you find the element. Hmm. Hey, I think that's why we didn't have to do the seal in here what we did here. Because we let's say we didn't find that number using the bisect, we're gonna use the right of that. So the largest number doesn't matter because the largest number that gives us a product that is less than or equal to the target. Yeah. So we have the one. So we're checking every single number in number one, and then we get the wait, no, 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 no. Yeah, yeah. And then we try to find the matching product that will get us to the target. And then in this case, we want to get all the numbers. If I might search to find the largest num2, where the product of the number is going to be less than or equal to the target. But why did we do right of that one? Is the smallest number that will give us a product that is less than or equal to the target. But if we go to the right of that point, we might go over the target, right? Or no? Let me see bisect right again. Oh, wait a second. Is it because it's one indexed? Oh my gosh. Because we want, okay, so we want the largest number that will give us in num2 that multiplied by the current num1 will give us an element that is less than or equal to target. So yeah, okay. So okay, so when we get to okay, that's why we did count plus equals that element because this is the largest number that will give us a product that is less than or equal to the target. So everything on the left is also gonna count to that number. Okay. Okay, so we pretty much we have a like every single product, right? And then we take the middle element, we check how many products we have that go up to the element, and then depending on that, we can either go to the right or go to the left. Yeah, and then updated the count. This is really hard. And then on the left, when a is less than zero, this is something that I don't understand. Like a, if a is less than zero, then if a is less than zero, be careful with the negatives. Okay, so we take a times what is b in this case? Yeah, I think it's the element in num2. If a times b is less than or equal to, oh wait, never mind. A times b is less than or equal to target, then b must be, yeah. If a times b is less than or equal to target, then the target must be greater than b, and then b must be greater than, yeah, that's right. Yeah. Target is equal to x by a. We add we do the seal of that, and then count plus equals to length minus the left y. So if the number is less than or equal to 0, binary search to find the smallest element in M2, num2, that the product of that element multiplied by the current number that we have is less than or equal to the target. Okay, because it's negative, so and then we're gonna do we have the whole thing, and then we find the bisect left, and we're gonna do the length of the whole thing minus this, so it's gonna be this. Yeah. So if it's negative, oh wait, we only want keep going negative, right? Yeah, okay. Because if we multiply negative by negative, we can get a positive that's greater than the target. So we always want to go to the right. Okay. Now I got that part. Okay. Um. Okay. I think I got that part. This. Oh my God. This is really hard. Okay. I think I got it. Okay. So it's pretty much you get the left and right, which is all the possible products that we want, right? Which should be like insane number, right? No, just say that. Yes. And then you go to the middle, and then that's the target. And then now we want to count how many products we have that can reach the target, right? So, so what we do here is, okay, so we have the target, and then we're going to count pairs. So if we have more pairs than k, that means that we have more pairs than k. We want to decrease that, right? So right is going to be mid. Yep, right is equal to mid right here. But if we have less pairs, If we have less pairs, wait, if count pairs mid is less than k, yeah, then oh, if it's greater than k, then we have too many pairs. So right is going to be mid. If we have less pairs, if we have too many pairs, oh wait. If we have too many pairs, we need to increase the multiplication. So that's what we do. Wait, no. Wait. Oh my gosh, this is hard. So if we have too many pairs that can go up to that target, we have too many pairs that can go up to that target, we want to decrease the target. So boom. Now if we have two, okay, we don't have enough pairs. So every pair is going to be less than, no, it's going to be greater. We don't have enough pairs. What do we do? If we don't have enough pairs, the low is going to be mid plus one. Why? We don't have enough pairs. Number one is greater than zero. What do we want to do? We want to get all the elements. If number one is greater than zero, we're gonna divide target by the elements. Now that's the element number two, and every number smaller than that will contribute to the answer. So we wanna grab all the elements that multiply to a number that go up to the target. Yep. But if the number is less than zero, this is negative, then we want to find the left of the number that multiply giving the target. Boom, everything's right. Oh my gosh, dude. Okay. Um, Now I don't think I. Let's see. Compute go count the. If count less than k, the kth smallest product. This doesn't make any sense to me. If the count is less than k, what that mean? What's that mean? That means that the number of elements that's less than or equal to the target. Oh, so we need to increase the target to give more options. Is that right? We need to increase the. Oh my God. Okay. Oh my God. Okay. So if we don't have enough counts, that means that our target is too low. So we need to increase the target to give more options. We always trying to find the products that go up to target, including the target. Okay, okay, okay. hmm Okay, I think I got it. So let's go over it one more time. So we start with two numbers, we get the target, and then we count the number of paths that goes up to the target, including the target. If we have too many pairs, that means that we can lower our limit to find less pairs. So right is equal to the mid. If we have too few target counts pairs, that means that our target is not large enough to cover a larger range of options. So that's why we need to increase the target. So left equal to mid plus one. Now how are we going to count the pairs? If for each number in num1, if that number is equal to zero, that means that no, actually, okay, so for every number A, we're gonna find the target that we want, right? In B, in num2. If the A is equal to zero, then every target, let me see how do we deal with the zero part. If A is equal to zero, oh, then we x is equal, this, sorry, if x is greater or equal to zero, then we can add everything because it contributes, yeah. Yeah, that's right. Okay, if if A is greater than zero, we want to find the first element, the largest elements that multiply by this number will give us the target. Take the largest one of that. And when we want to include that element, boom, and then we take everything to the left. Now, if the element is less than zero, we find the element to the left, not including that one. Oh yeah, we also include that one. So we go to the left of that one target and grab everything to the right. And then why don't we do seal with both? Because if a is greater than zero, so we're gonna find the element, we're gonna go to the left right of that and grab everything right here. Now on the left, so it doesn't matter, right? Now on the left, oh, that's why we might go here, right? When we do this this is the floor. Yeah, this is the floor. That's why we need to take this. Okay, let me try to kill this thing. I'm not very confident, but let's see. Okay. Okay, I think I got it. Let's see. Okay. Uh, okay, so let's do def count pairs. That would take the target, and then we can implement this later. Then we can do left, right is equal to, let me do anything is equal to 10, 10, and then left's going to be a minus n, and a, left is less than right, mid is going to be left plus right, do, oops, it count pairs mid is less than k, that means that we have too few, we don't have enough pairs, so we need to increase our, so left is equal to mid plus one, else else we have too many pairs, so right can be equal to mid. Okay. And this is also the case where k might be equal to mid as well, right? Okay, actually, no. I mean, the count of pairs can be equal to k. That's why we don't skip mid. Okay. And at the end, oh, we return, can you turn left or right? Doesn't matter, I think. Now for the count, what we're going to do here is count equal to 0. For a nums 1 and nums 1. Okay, so if num1 is greater than 0, and if num1 is less than 0, if num1 is greater than 0, then the target is going to be oops, and 2 is going to be target divided by 1. That's the number that we're looking for on num2, but we want to grab, since it's positive, everything that's less than that multiplied by the number, then by num1 will also give a valid answer. So we want to do count what count pairs, oops, count plus equals bisect, I don't even know what's where's the bisect, no, bisect thing. What was the, I don't even know. Bisect, no, I don't even know where important. Bisect up, I think I can do this. Bisect, oops, oops, why do I have this, I don't know. Oh, from bisect or bisect left, bisect right. Yep. I think I can just do, yep. So we want to find the first element. So let's say we have 0, 1, and then the first element is 1. And then we want to add the count. Okay, so bisect right, none 2, and then and 2. If count is less than 0, then we want to go every number. So that's negative. So everything that's greater than the first element that multiplying give the target will also be more and more negative. So that's fine. So everything on the right of that one. So we want to do this left. So what's the target? So 2 is equal to the target. I'm gonna do this first, but I know this is not right. I need to do the ceiling. I want to realize, I want to figure out why do I need to do the seal here. So choose go to this. So count plus equals. We only want the right side of that. So the length of num2 minus bisect left num2 2. So why do we need to take the seal of this thing? So let's see, we want to do the left. Boom goes right here. Why do we need to take the seal of this division? Hmm, I don't know. Because we find the first element and multiplying we give the answer, we go to the left of that. But if we take it consider, we might go to here, but we want to go to here. But on the right side, we take that one, we can go here, and then we go here, but we're gonna go here. I don't know, why wouldn't we just take the ceiling of both, honestly? math.cu. I think it's capital M, right? Wait, I have to import this thing. Yeah. Okay. Because like, I mean, in the right side part, I can go here, and then when we take the suit, that's not gonna be good, right? Go count this. Maybe we don't. Do we actually need the ceiling of this? I think. So the target number, let's say the target number is, let's say the target number is like 2 times 4, but -8 divided by 2 is going to be 4. But what if that was like 3? Like the ceiling we're going to include 4, but let's say that we include 4 with something that we don't actually want. But when we get to the right most element that multiply give you the answer, if we don't have that exactly number, we might go down 1, right? And then when we take the right, boom, it includes that 1. But the left will be 0 index, and then the count's not gonna be right. Okay, let me try that, and then we can debug later. But else, okay, else is equal to 0. So if target is greater or equal to 0, then count plus equals, oops, length of num2, because every single number contributes. If the target is greater or equal to 0, then 0 multiplied by any other number num2 will be equal to 0 as well. So I think this should be fine. Da, 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 da. Yep, return count. Let's see. Okay, am I off by 1? 7, but it's, how did we get, what did I get 7? Or maybe, let me try something like this. Boom, boom, boom. Oops, still in the wrong one. So I think oops, we might only need to do 182 maybe. Oops, didn't want to do that. There you go. Oh my gosh, I didn't want to do that. Okay, there we go. Now why? Why do I need to do this part? Oh, never mind. Actually, why do I need to do this part? A times B is less than or equal to X, then X must be equal to B. Yes. And then B must be less than X divided by A. Yeah. A, A times B is less than or equal to X, which is greater or equal to B. So B must be equal to the ceiling. I don't understand the ceiling part. Why do we need to take the ceiling? Okay, let's try to imagine the scenario. Okay, so we have a for each number, we have a target. The target that we need to find it on num2 is going to be this target divided by num1, which is the current number that we could have. That's the target at 1. But this target might be a float, right? The division might not be perfect. So if the number is greater than 0, then we want to find, we just take the floor of that. We take the floor, but we bisect it right. And then, so, okay, so let me try one thing. What if I do 0 here, and then we bisect left, and then here we don't take the 0, and then we bisect right. That work as well? Oh, no, that doesn't work. Did I? Hmm. So what? Let's see. If n is greater than 0, then we want to find an element that are here at this point. It's going to be so bisect right. So we want to include the element. Yeah. So the next element will be already greater than the multiplication, the target. We don't want that, but we want to. Okay, so that's the elements. We're gonna put it like that. Okay, so we're gonna write something. Now, so target divided by 1. Okay. So we want the target, but we want to do something smaller. So let's say, and let me copy this code actually, so I can draw. Okay, so let's say we have the numbers, and then after target, let's say it's going to be float, and it stays like maybe like right here. But we want the largest element that multiply by this. Okay, so yeah, we can't take the ceiling. This is fine because then we don't want this, right? We want to do this, but we're gonna bisect right. So boom, go to here, but we're gonna only grab everything from here. Now let's see the. Oh, what? I don't want to take the ceiling of this. Uh, this. Yeah, all right. Now why do I need to take this one? Okay, so let's say we have the same thing. Now we divide. We want every, so if it's negative, then we find the smallest number that multiply this giving the target, and we can, the target, but target can be right here, right? But we want the ceiling, so it will give actually this number, which is fine. And then we bisect left, yeah. Which you go here. Okay, that makes sense now. Because we can here, but this is already part of the answer, right? So that's why we take the ceiling and then we bisect the left. Boom, grab the whole thing right here. But on the positive case, let's say we fell over here, we can't take the floor of that because that gives us here, this is already part of the answer, and then we bisect right, we're gonna move here and grab everything on the left. Now I got it, why do we do it this way? Now, why it doesn't work switching those, right? Because if I go here and I take the ceiling, if let's say and the number is greater than 0 and 1 is greater than 0, then if I take the ceiling, I will go here, but this is not part of the answer. and then I bisect right, so I'm including something that I don't want. And then the same thing for the negative number. If I take the floor, yeah, if I take the floor, the negative number, I'm going here. This is not part of the answer. And then I go one more, which is bisect left. So I'm grabbing one extra element that should not be in the answer. Say, okay, now I think I got it. Hey, man, let's see what this one goes. Right. There you go. Really hard problem, in my opinion. The solution wasn't that bad, but understanding like why do we need to floor one and seal another, bisect right one, bisect left another, that was really hard. And then actually, this was kind of complicated as well. Like, what do you do if you have more or less pairs? But then you will need to understand what are actually left and right. And then, yeah, I've done a couple questions where you have like all the possibilities, and then you use binary search to find the actual answer you want. Instead of like thinking about this way of like, oh, you have an array, you have the two pointers, and then you move for two pointers, blah 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 blah. So yeah, really hard problem in my opinion. Took like 2 hours to just almost like understand the solution. So yeah, I'm gonna cut it over here. That's all I have for this one. I appreciate y'all for watching, and I see you guys next time.